Let's do this AP Physics 1 FRQ. We have a simple pendulum consisting of negligible mass and a small sphere as shown in the figure. The sphere has a mass of m and the center of mass is located at a distance L from where the top of the string is attached to the ceiling. So the diameter of the sphere is negligible relative to the length of the string because that sphere is just so small. And the sphere is released from rest from the string having an initial theta initial from the vertical, which means just a vertical line. So we have a second pendulum and an identical sphere is attached to a longer string than the sphere that is used in the original pendulum. So the sphere in the second pendulum is released from rest with the string having the same theta initial from the vertical as the original pendulum. And we want to know how the speed at V2 of the sphere is going to change and compared to the maximum speed V1 of the sphere in the original pendulum. Okay, so what we know is that the second pendulum is only going to have a longer string, but it's going to be released from the same theta initial. So because the string is longer, that means that the sphere starts from a greater vertical height above the bottom of its swing. So that means it loses more gravitational potential energy as it swings downward. So one of them is going to be up here, one of them is going to be also long, but it's going to be here. So that's H, and then this is H, when you compare them to a same reference line here. So what we can see is that lost gravitational potential energy is going to become kinetic energy. So then the sphere with the longer pendulum is going to have the greater maximum speed when it's at the bottom. So that's why our V2 is going to be greater than our V1. Now, consider the original pendulum in the case where the string makes an initial angle theta initial from the vertical. Starting from conservation of energy, we want to derive an equation for the magnitude AV of the sphere's acceleration at the instant where the string is vertical. So we want to express our answers in terms of these variables, and let's start with this. So our string, we are going to have that length L as our hypotenuse, and we can create a right triangle. So if we draw that vertical there, we have a 90-degree angle. We can see that our length of our string is going to be the hypotenuse of this right triangle. And this vertical right here, that is going to be our adjacent side. We can relate our hypotenuse and our adjacent side using cosine of theta times our length of our string. So when it's at its very bottom, it's down here. And there's a change in height. And we can find that by taking the length of our string, which is still going to be the length of the string when you're down there. Because it's going to pull the string down to that length, right? And then we can subtract our L cosine of theta, which is that vertical distance. We can factor out our L right here. And when we have L1 minus cosine of theta initial. So then we can take that. And then we can write our conservation of energy equation here. So on one side, we have our point where we're up. And then this one where you're down at the max. Minimum, I mean. So your initial potential energy cancels out as 0. Or your kinetic energy, I mean. And then you have your U initial, and then KF, and then UF cancels out as 0. So you have your mg delta H. So your delta H, you can plug in right here. That L times I, or 1, minus cosine theta initial. So that's this expression here. Then we can set that equal to 1/2 mv squared. We can cancel out the mass, and then we multiply both sides by 2 to get rid of that 1/2. Then we get v squared down here is equal to 2gl times 1 minus cosine of theta. So now we can do some centripetal work. So at this point, when you're at the very bottom, you have your tension force that's still acting upward because the string's pulling the mass upward. And you have your m2g, your force of gravity, still acting downward. So in order to find our force of radial, we have our mass, our sphere, times the acceleration in the radial direction. We know that's going to be equal to v squared over r. But here the radius is just the length of the string. So we can replace that. So upward we have the force of tension, and downward we have mg. That's equal to mv squared over L. So we had v squared earlier, and that was this expression here. So we substitute that in, and we get this. So we can see that our mass canceled earlier, right? We don't even have mass in this equation. So our answer doesn't depend on our mass. Now, what we can do is move on to our next post. We have, using the equation you derived in part B, indicate whether the sphere's acceleration at the instant the string is vertical is greater than for the original pendulum, greater for the second pendulum, or the same for both of the pendulums. And we want to describe how the equation justifies our claim. So we had for part B, the AV is equal to 2gl, 2g times 1 minus cosine theta initial. So we have no L in this equation. So no L makes sense because both pendulums, we had that they were released from the same angle, right? It was theta initial. Changing the length of the string doesn't change the angle. And we have the same G, theta initial, and these are just the same for both of these situations. So that means that AV2 is equal to AV1. So even though the longer pendulum has a greater maximum speed, it's still moving in a circle radius. And those effects are going to cancel because A is equal to V squared over L.